Thank you. Before we start, I need to acknowledge Jan Beekers and also Elna in the back. This is a team effort. Terry Newby used to be on that list. He's not anymore. He wisely migrated from the ARC. Okay, it's a project we do for environmental affairs, more specifically working for water. Our job is to provide a map of major invaders for the country. Those are species that are widely spread across the country at quite high densities and therefore must be treated in contract areas by working for water. The area that we cover is South Africa, Lesotho and Swaziland. It's 127 million hectares and therefore fairly extensive. We need to go down to at least a quaternary catchment level, of which there are almost 2,000 in the country. And then we started phase 1 in 2005. That was completed in 2010. And I'll go over that quickly because it's related to phase 2 that we currently dealing with. The characteristics of any map is, in my opinion, threefold. One is you need to apply or provide at least the scale of the map, therefore for the user to know up to what level he can apply that map. And it's often an aspect of any map that's abused. Secondly, you need to add an accuracy of the map, so that any user that applies that map for whatever reason knows how accurate that map is, what is the variation. And then thirdly, instead of focusing on a pretty picture on the map itself, your focus should be on the methodology. The reason for that is it will allow you to repeat surveys over time. In other words, to be able to monitor change over time. And that's where we want to head. We don't want to produce necessarily pretty pics, but rather a monitoring approach. We looked at the different options, completing inventory or mapping as one. Fairly expensive depending on the scale, about 300 million rand. You go down to a complete random sampling design. Once again, you're going to invoice somebody with about 100 million rand. Obviously with this you've got time and also expertise limitations. You're not necessarily going to find the people to spend that amount of time in the field. Our approach was one therefore of stratified sampling design. Using an environmental gradient, we determined what environmental aspects contributed the most to species occurrence. And the rationale was that if you sample along an environmental gradient, you will detect the maximum variation, in this case in terms of invasive alien plants, and you will minimize your sample points as well as optimize the results. We simulated sampling to determine or provide an indication of X amount of points will give us what results. And we eventually put out 74,000 sample points. We did an aerial survey flying to these points. We had observers in the aircraft, and then they provided an indication of what you find at that point. For instance, this is a Kotzè cyclops. Agala's plane, that's the reminders that you see in the background. Data was analyzed, and a number of maps was put out. And we provided two layers, namely a landscape layer as well as a riparian layer. And as Dave pointed out, Kruger was not surveyed. We had discussions with them, and they're in the maintenance phase. So they said we can rather allocate the points to other places. It was obviously a major disappointment for all the observers. The Northern Cape area, we did a transect flying the area, and we decided we're only going to survey the riparians. And that's where, as Dave pointed out, you see that clear-cut line. We used the Lesotho and Swaziland map to determine that boundary. Looking at the accuracy, what we did is we randomly selected 200 quaternary catchments, and we surveyed them more intensively with a regular grid. And under that regular grid, you had your Kotzè landscape survey that was applicable for the total study area. So the red line here represents our total invasion for the country, and then you've got your 200 randomly selected quaternary catchments, and you can see we've got an overall accuracy of R-square value of 0.8. Obviously you can improve this by playing with the figures and relating per quaternary catchment our results. With phase 2 we were tasked obviously to repeat phase 1 to start with the monitoring phase of the project, and then also we need to spatially refine our product. to go down to a management unit clearing plan level. And once again, if you look at level 1 or phase 1 of the project, you can see the broader landscape mapping that we did. It provides you with a good indication of what is where. For instance, I had the privilege of staying for 2 years in the Work Nature Reserve that's down here. And you get a fairly good indication of what is where, species, densities, etc. And then the dry areas we covered with the riparians as well as in the wetter areas, and these are these long worms. So the rest of my talk I'll split between landscape and riparians, and it will be pretty pictures. When we started in 2005, we basically had almost no remote sensing data for the country. We had a Landsat layer that was used in the land cover exercise. That was 2000, so it was already 5 years outdated. Spot was still in the planning phases. There was no spot layer for the country. Aerial photography, there was limited aerial photography for the Western Cape. I'm talking about RGB, color aerial photography. The rest of the country, portions were in black and white. Starting 2010, we had the privilege of having about 5 years of spot data, and we had aerial photography in color for about 2/3 of the country. And as with any project, you go through an evolution, and what happened here, we eventually ended up going down to tree level. This is in Nagalas Plain. It's an area of about 6,000 hectares, fairly small. And what you see here are trees. They could be licodendron bushes, indigenous, they could be invasives, they could be a combination of the two. But structurally you can see the difference between these larger vegetation groups and your typical fynbos around it. And aerial photography doesn't allow you to do spectral classification of it. It's not geared for spectral analysis in any way, image classification. It's more pretty pictures. It's a brilliant reference source if you're not in the field. And that's the intention of the product. And we said that if we can see the difference between the trees and the surrounding environment, somehow you must be able to pick it up. And we developed a moving window approach using neural networks, more specifically SOM, or self-organizing maps. And we started pulling out the trees. We automated the process. It's a fairly lengthy process. You're looking up to about 5 days to do a 1 in 50,000 map sheet. But we picked up the trees, and what this allows you to do, I think for the first time, is to come up with a standard set of rules. Where in the past, if I was to provide this to 10 experts with a tree cover, they will come up with 10 different maps. If I was to say, draw polygons and add densities. Now you can say to the machine, trees X amount of meters from each other, and say polygons half a hectare and more. Draw me a line, and it will provide you with a polygon. So 10 experts will come up with exactly the same map. The second thing it allows you now is to go and recalculate your density within these polygons. So you tell the machine to do your density estimations instead of, once again, 10 experts will come up with 10 different density classes. However, we still don't know whether this is indigenous or aliens or a mixture, and that's where the field work comes in. You must go and verify this in the field. We brought in three rules, 3 layers. The first one was obviously the most dense, and then we brought the light green in that was less dense, and the third one, the least dense areas. We used the working for water classes for that. Aerial photography for the country, as said, we've got about 2/3 available. That's the green parts. The purple is what's still in the production line. It's been flown, but we're waiting for it to come out. And obviously, Swaziland and Lesotho is not covered by our taxpayers, and hopefully we will hopefully get aerial photography, but not with our money. Looking at the riparians, this is a spot image. Multispectral 10-meter resolution, also the Nagalas Plain, and you can see the riparian vegetation here as bright red compared to the rest of the landscape. Now with the previous survey, all we had was a line shapefile from the Surveyor General, and what you see here are your perennials as the darker blue and your non-perennials as the light blue, and we buffered the perennial rivers and surveyed them. So you can see it's a coarse estimation of actual area, and it's an assumption, so you will be wrong in most areas. But that's all we had. We had a line shape file, we had to buffer it, and we added intelligence to these buffers by surveying these areas. So you have invasive intelligence, but what was lacking was your actual riparian delineation, the actual impact of water, low-lying areas on vegetation. And with the spot data that we've got available now, we can pull that out. So you can start to map actual riparians. And I'm going to zoom into an area down here. Back to aerial photography, and what you see is the riparian zone going down here. This is palmite. You see at a landscape layer the different trees, and then you see the trees around the riparian. You pull it out with your tree layer, and then you add your riparian layer. And this allows us now to start to look at tree densities within riparians, using your riparian zone as a summary unit, and to look at change over time in terms of tree density. Still, you need to go to the field to determine whether it's indigenous, aliens, or a mixture of the two. In conclusion, phase one, the map for phase one is in the background. You can see it's fairly coarse compared to phase two, that is here. This is a full aerial photograph that we've classified. It's 5,000 hectares in total size. And looking at phase one, what we basically did was to look at coarse and then effect in terms of coarse. So you determine what environmental gradient or what environmental variables contributed the most to species occurrence. You use that interaction to stratify your area, and within that area you then sampled for effect and provided an infestation per area. Now we've gone down significantly, looking at trees using aerial photography, coming up with little polygons like this within a larger area. Now this is 5,000 hectares. Imagine 127 million hectares like this. You have to summarize it, and you have to summarize it to something that you know that makes sense, and that's going back to coarse. So once again, we will measure effect being infestation within coarse, but at a lot more detail that is eventually then also summarized to a coarser layer as a second product to allow monitoring. So where we currently are with the phase or the project itself is to come up with a proper sampling design, because once again you cannot do a complete inventory. You cannot go to every single little polygon that's in there. You have to come up with a statistically sound survey procedure to deliver a map. Thank you.
Thanks, Ian. We've got 2 minutes of questions. No questions for Ian?
Ian, I think I asked you this every time and I can't remember what you answered.
I know the question.
My concern, especially the figures that David showed, was how the huge amounts of acacias, pines and eucalypts that compared to what we had been recorded in previous years. How do you distinguish between plantations and invasion? Because I just feel that, like, for example, the eucalyptus, perhaps much of that is actually plantation. How much of it is actually invasion?
Structurally, you can immediately see the difference.
So you are, are then, so you are excluding what you see as plantation.
What we did with the previous round is we used the land cover map that was generated from 2000 data to exclude certain land cover classes. So all organized agriculture, plantation, urban areas, mines and so on were excluded from the data. This time we need to see how we're going to actually do that, because we haven't got an updated land cover product at this stage. But plantations, you can clearly distinguish between the two, and what we've done with the previous one as well is we did the survey in 2007. They used 2000 to publish it in 2005, the land cover. So obviously we had changes in plantation forestry. We allowed the data capturers to capture that it's a plantation or it's an urban area, it's a mine. So you know that point you can eliminate from your survey.
But when I've been doing surveys, as well, one of the problems is that, for example, acacias, you start off with the plantation, then it starts spreading. And then sort of how do you tell the difference? Where's that cut-off point? that what was originally started as a plantation and now you're getting that spread. So it's just all complications like that.
With the remote sensing approach that we use now, you can immediately distinguish between the two. The core plantation area, if we can call it that, is very different compared to that ad hoc infestation that spreads from that plantation. So you can separate the two. But, sorry, the previous 3 questions that you've asked me, my response at the end was always the same. You must come and fly with us.
I will.
Please.
A question at the back.
The same question in relation to indigenous forest and riparian forest. How do you distinguish?
I think at this stage we can't. Riparian, indigenous forest, milkwood, dense protea stands, we can say it's very active vegetation. It's of a very high density. For instance, on the Gallas Plain, with the imagery that we've got, milkwood, indigenous forest, dense cyclops, they all come out as similar. Field work will have to split the 2 or the 3 or the 4 classes for you. You can't sit in the office and say, this is now that and that's that. There's only one way, going to the field.
Thank you, Ren.